Welcome, guys. Yeah, so this is my second video about the Fourier analysis. So at least today we are going to prove some special case where the Fourier series will converge to the original function. And hope you guys subscribe to my channel. Okay. So if you haven't seen my previous video or haven't seen my mathematical analysis list, then I will post the list link below. Okay, so remember that we can define Sn of f comma x to be the partial sum n minus n c n is potential I n x, where Cn is the integral of this. Okay, and remember, so f is a function defined on minus pi to pi. Yeah, and to the real number, and f is integrable. Why f is integrable? Because if f is integrable, then Cn is well defined, then you can define it. Okay, so and then what I proved is that the previous theorem that I proved is that this square of this Sn partial sum will less or equal to 1/2 pi negative pi fx squared dx. Okay, so this is the preliminary results that I proved previous. Okay, so now let's introduce something which is more manageable to compute called Dirichlet kernel. Okay, so Dirichlet's kernel is also very simple. dnx divided by exponential inx. Let's say n is minus n to n. So easy to compute this by geometry series. So the results will be this. Okay, and you should easy to do the calculation such that proof this inequality. Oh, sorry, equality. Okay, so this is also simple. And yeah, so then now let's rewrite this partial sum Sn in terms of the Dirichlet kernel. Okay, so let me our Sn to be Sn to be what? Sn to be summation minus n c n exponential I n x can be written as n minus n, right? Put your coefficient. Nt dt is exponential I n x, right? Since you need to change it into t, so it's negative pi pi. So it's negative minus n 1/2 pi. Pull out integration, and f of x exponential I n x minus t dt. Okay, and since it's finite, so I can exchange the summation with the integral, and yeah, and yeah, you can pull. Oh, sorry, this is t, and then you can pull out this to be 1/2 pi. Pi negative pi f of t summation n minus n exponential I n x minus t dt. So this guy is the Dirichlet kernel with n x minus t. Okay, so results is that Sn can be written as 1/2 pi. Okay, so written as 1/2 pi f of t dn s minus t dt, negative pi to pi, and using the change of variable f of x minus t d dn t dt. Okay. Okay, so very simple. This is just change your variable. Okay, so now we have this. Or yeah, basically we have this. Okay, so now we can use this to prove the following theorem. Okay, so this is the first theorem about the condition one. I should say the condition such that the f will the same as Sn as n goes to infinity. So basically the triangle Fourier series will match to f. Okay, for some x, if for some x there exists the delta greater than 0 and m less than infinity, such that f of x plus t minus f of x less or equal to mt. So this is somehow like the Lipschitz continuum. So basically your difference can be bounded by linear by this t. Then that for all t belongs to, let's say, minus delta. Right, so and that means locally at x, where you're very close to x, the function growth of the x can be bounded by linear with this difference. Then limit n goes to infinity, this Sn will fx. These points will the same as f of x. Okay, so this is why we need to use the Dirichlet kernel. So let's give the proof. Proof is simple. Let's define g of t to be fx minus t, f of x sine t divided by 2. Okay, and this I only define right. So if t is 0, it blow up, right? So I should define this for pi. And I define g of 0. So I define, yeah, I mean you can define, so g of 0 is 1 if t is 0. Okay, so one property I haven't mentioned is that if you do the integration of this Dirichlet kernel, then you will get 1. Right. The reason is that only the constant term survive. The rest is 0. You can get 1. So that means let's say your s of n fx minus f of x. So the key is that you need to bound this guy, right? If you bound this guy, then you know you can prove that they are the same. So you want to try to bound this guy. So this will be 1 over 2 pi negative pi g of t right here times sine t what? So half nt dt. Yeah, this is right. So let's see what is true. Yeah, I guess it's here, right? Because this dn xt by definition can be written as this, right? So there is a sign here. So you just put everything you have, and you will get this. Okay, and then you just expand it, right? So we can g of t cosine t divided by 2 sine nt dt plus pi negative pi g of t sine t divided by 2 cosine nt dt. Okay. Stupid. Okay. So what? Okay. So then what? Then we need to then we should use a theorem, right? There's a theorem that I proved before called the Riemann-Lebesgue lemma. Riemann-Lebesgue lemma says that if you have an integrable function which should be bounded, you times the sine nt dt for any region, let's say negative pi to pi, and the limit n goes to infinity, then this guy will be 0. Okay, and then this guy can also be 0. Okay, so this is proof by this is using the previous proof. Okay, so now particularly this g of t is bounded, right? The reason is that this fx minus t minus f of x by definition is bounded by this guy, right? So you're doing this m of t bounded is sine t divided by 2. So this guy is bounded. Okay, so if your t goes to 0, it will not blow up, right? Because it becomes mt divided by sine t divided by 2. So this guy is bounded. Okay, so this guy is bounded. Okay, bounded. So by this theorem, if n goes to infinity, then these two terms goes to 0. Okay, so okay, so this is the first condition that you can make the Fourier series converge to the f of x. Okay. Yeah, let me just write down some corollary. So corollary says that if f of x is 0, and for all x in some segment J, then limit Sn f x 0 for all x belongs to J. Okay, so this I should say that the segment should be viewed as an open interval, I guess. So what it's saying is that if your f of x, which is 0 on particular open interval, then your Sn will be 0, right, for the interval. Okay. Yeah. So this is just follow from previous theorem because I mean, yeah, you already got this, right? So if your f, it becomes 0. Okay. And by previous theorem that you only care about the very local close to x, right? So which tell you that this is called the localization theorem. Okay, so that means what? That means Sn prop f of x, this guy, as far as convergence is concerned, depends. So depends only the value of f in neighborhood of x. Okay. Yeah. So yeah. So let's see another theorem which is very close to Weierstrass approximation. Okay, so remember in maybe a few videos ago, I proved the Weierstrass approximation theorem. So simple theorem is that for any closed interval AB, so any point, any continuous function f, if f is continuous function f, there exists the polynomial p of x, such that f minus p of x can be arbitrarily small, right? So this means that you can take sup can be less than any epsilon. So fixed epsilon, you can always find some polynomial which is arbitrarily close. Okay, so there's a theorem says that if f is continuous in the period 2 pi, and for epsilon greater than 0, and there's a trigonometric function, sorry, trigonometric polynomial. So trigonometric polynomial means that the summation of sine and cosine, which is just what we define, p, such that f minus p is less than epsilon for all x belongs to negative pi. Okay, or basically, yeah. Okay, so this is like the also the you cannot say the generalization because I think I proved that not just that you can prove more powerful Stone-Weierstrass theorem that I just previously proved, something like the vanishing null points and separating points and plus some property that you can do this. Okay, so let's give it a proof. Okay, so it's simple. Identify x plus 2 pi, then you can say that f is defined on a circle. Okay, by circle let's say S1. Okay, so by mapping x to exponential ix, right? So that means what? That means okay. And this is the first part, and also all the trigonometric function. So all the trigonometric function, as I say, the generalization of Stone-Weierstrass, you can easily say that all the all trigonometric functions forms a self-adjoint algebra. Okay, the reason is that by my definition, if you have a exponential ix, right, you go to exponential negative ix. So this is cosine plus I sine. This is cosine minus I sine, right? But my definition of trigonometric function contains both. So which is a self-adjoint and also algebra because you times any two. If you times any two trigonometric functions, suppose you sine mx cosine nx, then you can separate it into the, you can change it into the sign, pure sine term and another pure sine term. So the product of, right, so you see that the trigonometric function is closed. So any two trigonometric function Pn plus Qn will still be a trigonometric function, and the P times Qn will still be a trigonometric function. And then from here that we know that conjugate is also self-adjoint, right? So this forms a self-adjoint algebra. And then this is circle, right? So circle is compact. Okay, and plus that why is just saying that which is a separate points. So this is your exercise to prove that there is a separate this is separate points on T and the vanishing point of T. So I think I already proved it's self-adjoint and the circle, and you can easily show that this is separate points on T and the vanishing point on. So vanishing point on T is very trivial, right? Because I mean, you take any point, right? So one of the, I mean, if cosine is 0, then sine will not be 0. If sine is 0, then cosine will not be 0, right? So you can always find a function which is non-zero, and the separate point is also easy. Okay, so by the generalization of the stone Weierstrass, which I prove, I will post the link below if you haven't seen the proof. By the generalization of the stone Weierstrass of the complex value function. Okay, so by this theorem that we know that the trigonometric function, so basically the uniform closure. So the theorem says the uniform closure of the trigonometric function will become all a continuous function. Okay, that's it. Okay, so finally, let's give a famous theorem called the Parseval's theorem. I remember that I proved in this theorem maybe a while ago, right? But let's quickly prove it. So suppose this is the Fourier divergence. So suppose fg are Riemann integrable function with a period 2 pi. So let's focus on the negative pi to pi. And so I can write f in terms of, let's say, Cn is equal to I n x and from negative to infinity. Okay, so remember that I didn't say that f of x will be the least guy. I didn't say this. I only say that the Fourier coefficient, the Fourier series of f is defined to be least, and the g is defined to be least. Oh, by the way, and by the previously that I already proved these two will converge. Okay, then if you this 1 over 2 pi f minus Sn squared dx, negative pi to pi will goes to 0, Sn goes to infinity. This is first one. And the second one is the pi negative pi f bar g dx will be gamma n Cn bar. Okay. And the third is that 1 over 2 pi f of x squared dx will be summation Cn squared. Okay, so this one is usually called the Parseval theorem, the final one, the third one. Okay, and the proof should be very simple, just using the orthogonality. Okay, so let's give it a proof. And okay, let's define yeah, maybe the first one. Yeah, so the first one is yeah, the first one is should be the most non-trivial one. Okay, f minus Cn squared dx and goes to infinity 0. Okay. Okay, so let's define notation. Let's say I give you so-called L2 norm, which L2 defined to be 1 over 2 pi, pi negative pi, and the h of x d squared, and take a half. Okay, so let's say given epsilon greater than 0, and let's say f. So f is a Riemann integrable, and I know that the thing is periodic, so I have this. And by the previous theorem, or I think this is exercise. Okay, so you can find h such that f minus h is less than epsilon. Okay, so h is also a continuous function. I think by previous Weierstrass, I mean you can find this guy. Okay, so this is, and also so this h is a continuous function. Okay, and by the previous Weierstrass, you can find a trigonometric function, trigonometric polynomial p such that h minus p is less than epsilon for all x. Okay, so which you can prove that h minus p, the distance to norms, will less than epsilon. Okay, so let's say if p has a degree n0, right, degree n0, and yeah, okay. So okay, so yeah, let's see, this is my assumption. Okay, and by the previous theorem that I think we know that so h minus Sn of h, right, this guy will less or equal to h minus p, right? Because p is a trigonometric function arbitrarily close to actually close to at least epsilon, right? So this is previous theorem that I already proved. If you can pick h, so h Sn h will be the closest polynomial closest one compared to this p by the previous theorem. For all let's say for all n greater or equal to n0. Okay, and okay, so let me just write down. So remember that previously that we have this theorem. Say for any a b, your Sn of x dx squared is equal to cm squared. Let's say 1 from n that's equal to this. Okay, so I proved this in a previous video. Okay, so now I have this, right? So I can use, so I can replace h minus f to f. So what I'm saying is that let's see, h minus p. Okay. Okay. So yeah, so from this I put in here, I get Sn of h minus Sn of f to norm or equals to this is linear, so let's say this is n, so Sn of h minus f to norm, which is less or equal to h minus f to norm, right? By this result. Okay, so by minus h, right? By this construction is less than epsilon. Okay, so that means so you can combine everything, right? So you have what? You have f and h, and at SNH and SNF. Okay, and h and its difference, right? So you see you have the first one. Let me just write down. So you have the first one and the second one and the third one, right? So you can get your f minus SNF to known by using the three of them. So I think one is h minus its partial sum, and the final is its partial sum minus Sn of f. Right, and then you use, so it's less than 3 epsilon, right? So basically you prove that when epsilon goes to, if you pick epsilon to be small, that means you pick n to be larger enough, this n greater or equal than 0, right? So if you pick this epsilon to be close, very small, and then n0 to be larger enough, then this guy will converge to this Fourier series. Okay, so this is the key idea that you're right. So previously, okay, so the important part is that in the this theorem, I only proved that this trigonometric function exists for the continuous one, right? Because we need to use a stone Weierstrass. But in this theorem, I only require the Riemann integral. So it's tiny. There's a gap that you need to fill. So that means so that's why I have this theorem. Okay. Okay. Okay, so let's say prove the second and third. Second and third are almost trivial, right? So let's quickly do it. So if you want to prove this, you can do it by 2 pi, negative pi, and pi, and this is very simple. So this is just Cn exponential I n x g bar of x dx, and do it. And then you can do it. The so key is this is finite. So when you do this step, you can easily exchange you can easily exchange this integral with the limit. With the summation because it is finite. Okay, so. Okay, then by the orthogonality, this guy is to be gamma n, right? So this is become negative n minus n, Cn gamma n. Okay, and you can take, I guess you can take the n goes to infinity and this guy become yeah. Okay, so up to now we are very close. So final ingredient is the Cauchy-Schwarz. Let's give the final results. Right, so I want to prove these two are the same, right? At least n goes to infinity. So I need to use a Cauchy-Schwarz to bound it. So remember that I still don't say that S and F will become F. I never say this, right? I never say this. I only say that their square roots, their square difference integral will close to 0 as n goes to infinity. I didn't say Sn will converge to F. Okay. And I only prove in some particular case that we have such results. But up to here, I only assume that. So I need to bound this. Okay, so by your Cauchy-Schwarz. So I can bound this. Okay, by using Cauchy-Schwarz. Square and the integral of g squared. Okay, so let me a little bit sloppy. So become this. And this guy is bounded. This guy will goes to 0, right? By the previous first theorem. Okay, so then you just take and goes to infinity. Then this guy will close to 0. Okay, so which means what? These two will close to will be the same, right? So just take n goes to infinity, then take n to be infinity, so that this summation of this n goes to infinity become negative Cn gamma n will become Sn will be this. I'm not saying Sn become F, but I said the integral of this difference become 0, right? So this becomes this. Okay, and if you take G bar to be F, then you prove the third. So if you take, let's say, if you take G to be F, then you prove the third, just Cn squared. Okay, so let me just mention the key whole point. So whole point is that I never say that F will be the same as F Sn as n goes to infinity point wisely. I don't say this, but I can prove that their difference, their square roots, their square difference, their L2 norm close to 0 as n goes to infinity. So once you have this, then you can use the Cauchy-Schwarz to prove that their Fourier series, this guy become this guy, even though F and G will not become this. Okay, so this is the whole Parseval's the tricky part in the Parseval theorem that even I didn't say f will convert to its partial sum, but I proved that their square difference is close to 0 as n goes to infinity. Then I can use the Cauchy-Schwarz to bound the following. Okay, so you can see that up to here that we still didn't get the only have this theorem that I guarantee that pointwisely this Sn converges to f. So that means the Fourier in what sense then your Fourier series will be the same as your f is a difficult problem. And then maybe in the future that I will talk in the real analysis and extend this into generalization. Okay, so next video we talk about gamma function, and then we finish this chapter.